All right, let's take a look at a word problem, a real life application of using derivatives of, of periodic functions. So in this example, it says on July 7th, 2009, there was a full moon in the Eastern time zone. And if t is the number of days since July 7th, then the percent of the moon illuminated can be represented by this periodic function, which makes sense because, you know, the illumination of the moon is cyclical. So we first of all want to find the derivative of this function h of t. So let's do that. Let's find h prime of t. All right. So first we have a constant. 50 is just a constant. Derivative of the constant is 0. All right. So I'm not even going to write anything for that. And then we have a constant multiple of a cosine function, but then there's this constant inside of the cosine function. So, all right, so let's write 50, all right? So, and then we need to take the derivative of cosine, which is the negative sign. So I'm actually going to put the negative out here, and then we get this negative sign. We leave the inside function alone, so it's just going to leave it as pi over 15t. And then we have to multiply by the derivative of the inside function. We have to use the chain rule here. So then I'm going to multiply that times the derivative of pi over 15t. All right, so that's just going to be pi over 15. Pi over 15 is just a constant. And let's clean that up a little bit. I see that I can divide this by 5 and get 3. Divide this by 5 and I get 10. So I end up with a negative 10 pi over 3 times the sine of pi over 15t. All right, so there's my derivative. All right, now it says sketch a graph of h prime of t. Okay. All right, let's sketch that graph. It's just a negative sine function. So let's see. I'm just going to draw my axes here. So there's my axis, and there's no midline, or the midline is 0 essentially. So it's going to oscillate above or about the t-axis, right? I'll call this a t-axis. And the amplitude is 10 pi over 3, right? But it's negative sign, so it's going to go down first. And so it's going to oscillate between negative 10 pi over 3 and a positive 10 pi over 3. And what's the period? What's the period? Well, we can, actually, let's write this down here. So the midline we found is 0. The amplitude is 10 pi over 3. And the period is 2 pi over b. Remember, 2 pi over b. So we have 2 pi over 15. Oops, 15. Okay, which is basically 2 pi times the reciprocal of pi over 15. So 2 pi times 15 over pi. And you can see the pi's will cancel, and I get a period of 30. Period of 30. That's time, and my time is in days. All right, so this is a period of 30 days. All right, so let's graph that. We're going to go, for the sine is going to, if one period goes 30 days, we know that we're going to, and it's a sine function, it's going to cross the midline, which is 0, at 0 and 30. So there's 30. Then I'm just going to break my interval here into 4 equal parts. Okay, so here's 15 days, and this would be like 7.5 days, and this would be like 22.5 days. All right, so we're just going to graph it. It's a negative sign, so remember we're going to go down first. So we're going to come down here like this, and then go back up to 15 at the midpoint, back at the midline, and then we're going to go up to 10 pi over 3, and then come back down to we're at the x-axis again, or the t-axis. We're at the midline again at t equals 30. Okay, so that's a sketch of what it looks like, right? That's what our h prime of t looks like. All right, now it's important to understand the derivative, and not just but that's conceptually, what does it mean? What does the derivative mean? This function h of t represents the percent illumination of the moon, right? over time. So you can put in any value for days days since July 7th, and you'll get the percent illumination of the moon. So the derivative is telling you how that percent illumination is changing with time. All right, so it's important to understand that. So that and another thing that's important to understand is also the units. The units of h prime of t. If h prime of t is in percent, then h of t is in percent, right? So the units are essentially percent, which is kind of a unitless quantity. But the derivative will be in percent per day, right? Because we're looking at how that percentage is changing over time, and the time is in days. All right, so let's take a look at part C. It says for the interval from 0 to 30, t equals 0 to 30, when is h prime negative, when is it positive, and explain what those values mean. All right, well, we can just look at our graph. It's below the t-axis, right? The graph is below the t-axis. Between 0 and 15, right? So first 15 days, h prime is negative, right? And so what does that mean? It means that the percent of the moon illuminated is decreasing during that time, right? Because the derivative is negative. All right, so when the derivative is negative, then that means that the original function is decreasing. So the percent of the moon illuminated is decreasing during this time period. So let's look at what happens. Where is this function positive? It's positive between 15 and 30. And when the derivative is positive, that means the original function is increasing. And so that's telling us that during that time period between 15 and 30, the percent of the moon illuminated is increasing. All right, so let's take a look at when the derivative is 0. When is the derivative 0? All right, now there's a few different time periods, actually. Let me keep this on here, I guess, so you can see the graph. So the derivative is 0 at here, t equals 0, right? T equals 0, it's crossing the x-axis. So I'm looking for when the derivative is 0. This is the derivative. I should probably label this. This is h prime of t. All right, and it's also 0 here at 15, and it's also 0 at 30. All right, so to answer the question, h prime of t is equal to 0 when t is equal to 0, 15, and 30 days. All right, so what does this tell us about the moon? Well, let's take a look at the graph. Now you can imagine this cycle is going to just continue. So if I extended this beyond, it's going to continue like this, right? So you can see at t equals 0, the derivative is positive and then it becomes negative, right? It's above the x-axis and then it goes below the x-axis. So that means that the original function, h of t, the illumination of the moon, is going from increasing to decreasing, all right? So it's also happening here too. It's going from increasing above the x-axis to decreasing, right? That's the original function is going from increasing to decreasing, right? Because the derivative is changing sign at that point. So at those 2 points, it's going, like I said, it's going from increasing to decreasing. So essentially, you've reached maximum illumination at t equals 0 and t equals 30, which is essentially meaning that it's a full moon. Okay. All right. So the original function, which is the percent illumination, goes from increasing to decreasing. So we've reached maximum illumination at t equals 0 and 30, and we have a full moon. Now let's look at the other one at t equals 15. When t is equal to 15, it looks like it's going from, the slope is going from negative to positive, right? Because h prime of t is going from negative to positive, which means the original function is going from decreasing to increasing. Okay, so essentially, you know, that at t equals 15, we have the minimum illumination, and the minimum illumination of the moon would be the new moon. So let's write that down. So at t equals 15, we have the minimum illumination, which corresponds to the new moon. All right, well, that takes care of all of the examples for this section. And take a look at the discussion questions, and I'll meet you in class.